Okay, I want to talk to you now about rotational kinematics. So what we do now, excuse me, what we now know, we understand what the period is. The period is seconds per rotation. And the frequency is 1 over the period, just like it was in waves. And that's the number of rotations per second. Okay? And we're going to deal with these new things. We in regular kinematics and linear kinematics, we dealt with delta x and v and vi and v final and a. And we're going to deal with those same things in rotational, but they have different measurements. So if I'm going around a circle like this, think of a wheel going around, right? We can talk about how far that wheel went around, not in meters as much as in degrees, or we like to use radians. Why do we use radians? Because if I know the radius, if this is 3 meters, 1 radian is an angle where the distance around the outside is equal to r. So it makes the math a whole lot easier. You're going to see that. We don't have to go between degrees and radians very often. In fact, very, very seldom. But it's just a conversion, and I'll show you that conversion later. So let's talk about this. So we have all these different variables. Well, there are all these equivalents in rotation. So instead of talking about how far something travels in meters, and when we talk about rotation, we're going to talk about how far this point travels. That would be the d there. And sometimes we call it L, kind of like a lowercase l. I'm going to go in between those. I know it's L on the equation sheet or on the unit sheet. The equivalent to that, the analogy to that, is this delta theta. That's an angle, how far it moved. So you can think of that like an angular or rotational displacement. Angular displacement, angular. I'm going to write that up here, angular. And we measure that in radians. Okay? Then we say, oh, this thing is going around, and it's going so many meters per second linearly. Well, we have an equivalent of that that's called omega, angular velocity. The angular velocity. And we measure that in, instead of meters per second, radians per second. And we can do all this, the same sort of things that we did here. We could have an omega initial, an omega final. For today, I just want you to concentrate on this stuff. Okay, pretend we're talking about constant velocity like we did in the, I don't know, unit 2. So it's easier problems. Well, think of this. If average velocity is displacement over time, and we're just going to use d over t, because again, we're talking about these curving things. They're not really vectors in the linear sense. So we talk about tangential velocity is how far around the circle it went divided by time. Well, the average angular velocity is just going to be the angular displacement, how far it went, what angle it went through, divided by time. In fact, you're going to see, again, this is just kind of foreshadowing here, all these equations that we had with these, we can use with these. So for example, don't focus on this, but for example, if you had delta x equals VIT plus 1/2 AT squared, it's no harder here. We can just do delta theta equals omega I times t plus 1/2, and they call that a alpha, 1/2 alpha t squared. So we don't have to learn any real new equations. We just have to learn these new variables. Okay? So what I want to do now is I want to take the first problem on page 2 in the packet, and I want to do that for you. And it says, a ball, radius is 0.2 meters, spins around 5 times in 8 seconds. Okay, find how far a point on the outside moves in 1 minute. Well, one thing we want to do is that if you look at the table that I've set up for you, frequency, period, and then linear stuff and angular stuff. I want to teach you, there's one trick in here that you need to do. It spins 5 times in 8 seconds, so the frequency is going to be 5 rotations per 8 seconds. And we could put that in hertz or in rotations per second. I'm going to leave it as rotations per second. Period is 8 over 5, 8 seconds per rotation. And 5/8, if I do my math correctly, I think it's 0.625. And this ends up being 1.6 seconds per rotation. Now there's something I didn't tell you that makes going between these things easy. Well, actually I did tell you, but I didn't broaden it. If we go back up here, the relationship between the linear and the angular is this. The linear is always the radius times the angular thing. So the linear distance is going to be r times the angular displacement in radians. The linear velocity is going to be r times the angular velocity in radians per second. But we have to have it in radians for this to work. Okay, so here's the way we get from this material into here. Frequency is how many times per second. But we know that every rotation has 2 pi radians. So we really want this to be in radians per second to go down here and be an omega. And again, I've put these things in on the in the packet so you can see how this works. So I want to get this, which is in radians per second. Well, that's easy, and let me actually even put averages over that. 0.625 rotations per second times 2 pi radians per rotation will end up giving you the number of radians per second. And when you punch that in, 2 pi times 0.625, you end up with 3.92 radians per second. And that's just your average angular speed. All we did was do a unit conversion. Then remember, this times r gives you this. So v equals 3.92 times the radius, which is 0.2, and you get 0.785 meters per second. So we know it's going around at some angular rate, and we can figure out how far a point 0.2 meters away is going to be traveling. It ends up being 0.785. Then we said, and sorry I didn't write this down, the time is 1 minute, 60 seconds. So we really just say average velocity is distance over time, multiply that by 60 and we get 6.28 meters. Multiply this by 60 and you get 31.4 radians. Okay, I'm going to stop and I'm going to let you do the rest of page 2.